They were expecting to carry fuel tanks inside this tunnel. So we had to design for a huge fire, and we were able to keep the smoke unidirectional using this system. Here you can. This fire curve is now declining. It is now in the declining stage. So it is completely for 60 minutes that the fire runs. Now the fire is about to decline, and this is how the smoke moves. For underground parking areas, we model, this is the typical model of underground parking area. Then we have these green areas are the fresh air inlets. Red is the exhaust. Blue is a natural inlet. It doesn't have a fan. Green areas have fresh air fans. Blue is a natural inlet which is open to the atmosphere, and it can naturally, air can come in. There is this car here, and these are the jet fans, which is alternative to duct ventilation, are installed here. The thing about car parking is for a duct ventilation, you don't need CFD that much, because duct will guide the smoke the way it should go. But for a jet fan, if you have to use, then to ensure that the jet fan directs the smoke in the right direction, we need to do CFD analysis. Otherwise, the design might not be good. So here you see the velocity results, how the velocities are developed. This is just the exhaust fan is working and the fresh air fan is working. So this is how the smoke is. Now when the jet fan starts, this is how the velocity is developed inside the car park. This is with the time. And now in this case, if a fire occurs, this is how the smoke will move. We have to ensure that the visibility is maintained in at least 70%, 60% to 70% of the area of the basement. Here you see only this area, this fresh air is making sure, this fresh air source is making sure that in this area visibility is decent. And actually there is a fire exit here, so people can run out from here with a decent visibility. The visibility in this area is around 10 meters to 15 meters. And here the visibility is very less, it's less than 5 meters, which is not good. And this area is, we are able to make completely free of smoke using this design. So that's one of the example of a good design ventilation. Here you see a example of a badly, despite so many fans, despite so many fresh airs, exhaust, the location of fans is not so that it can exhaust the smoke in the right direction. It fills up the whole, almost the whole basement within like 500 seconds of the area. The whole area is filled with smoke. It's not a good ventilation for this. Here you see a very good compartmentalization or zones that are defined in this car parking area using these jet fans here. These jet fans are able to keep the smoke fire in this zone only constrained up to this zone only. So there is not much smoke going, and also this is very light smoke, so it doesn't matter because visibility is good in this complete area. So whole of the smoke is constrained mostly. This is also a huge, it's a reasonably large fire. 3.1 megawatt is the fire intensity, which is standard, also specified in standards. Here is the exhaust, red one here. This is fresh air, natural fresh air is being taken from this direction and this direction. And these jet fans are directing this fresh air to this exhaust. Okay, I have an example from a project we did in South Africa. It's a Blue Route Mall. It's still under construction. This is a 3D model. There was a discussion that since it is open from all the sides, it might be possible to vent out the smoke without using any ventilation, because it's not really like a basement, because it's open from almost all these green areas were open. So we did the CFD to see how it works. This was the 3D model. We modeled the drop beams, everything. This was the 3 meter, all the columns were modeled. This was the car source of the fire here, and location of the fire, natural vents all around. And when we did this, okay, there's some problem. Microsoft always gives you some problems. In this simulation, you can see how the smoke is spreading in the complete basement. Although visibility is maintained here, but in about 200-300 seconds, the complete area is filled with smoke. I think this can be very well directed to constrain in a particular zone using mechanical ventilation. We can do that. We can keep that in a particular zone. We are right now working on designing the system so that we can keep it in a particular direction using just natural ventilation and jet fans. So just to give you an overview of the software tools used for conducting CFD studies, a lot of development has happened in last 1 decade in this area. A lot of new and effective software tools have come up. FDS is developed by US Department of Energy specifically for fire and smoke simulation using large eddy simulation, which is a very powerful tool. It's a very effective tool for fire simulations and smoke simulations, and its user interface is not so good, but the results are really good. We have validated those results experimentally as well. Fluent is a general CFD tool which is also used in other applications like aerospace, power sector and all. It uses finite volume method for numerical solving. And this is also a good tool, but you have to work a bit more in specifying your geometry because it is not customized for fire safety. Then these are other tools available. There is also a lot of open source tools available, like OpenFOAM is a open source CFD library which you can customize and use according to your requirement for fire and smoke applications. Fluent and FDS are the most popular tools for fire simulations. Even most of the standards, US standards, NFPA and all, specify FDS as the tool to use for the simulations. The simulations I showed you were mostly on FDS, apart from the airport simulation that was on Fluent. So it's a nice visualization it gives. Yep. Thank you. If you have any questions, you can take it up.